So this talk, it's on the application of some methods from machine learning to a class of models, discrete-choice models, which are frequently encountered in empirical work, in econometric work, in economics. And so these are discrete-choice models. And so discrete-choice models, they're a kind of workhorse model for modeling demand in many areas of economics and also marketing. And recently, there's in these areas in economics and marketing, there's been access to a lot of higher dimensional data. So this might be data coming from firms like Amazon, eBay, and so on, or they might be just large databases coming from traditional retailers. So not necessarily tech firms, but there's access to a lot of transaction level databases from traditional retailers, like the supermarket data we saw in the first talk this morning. So, and of course, many recent applications of these models face the problem that, in trying to use these discrete choice models for estimating demand, there's a problem that the choice sets faced by consumers in these models can be very large. Because I just want to give some recent examples. Nick Buchholz, he had a job market paper last year in economics where he was trying to model, which locations in Manhattan the taxi cab drivers wait for fares. Okay, so there's obviously, there's hundreds, thousands of places that you can wait for a fare in Manhattan. There's also a paper on legislators' choices of language. And also restaurant choices in New York City, and also choices among bundles of complementary products. So these are all examples of situations where you might be trying to estimate a choice model where the choice set can be very large. Okay, and so that's actually the angle that I want to take in this talk, which is to try to address the use of machine learning tools to reduce dimension of large choice sets in a discrete choice model setting. Okay, so I guess I want to say up front that this paper is not it's not focused on another interesting problem in discrete choice models with large data, which is the possibility that there could be a large number of characteristics. So I think that was kind of touched upon in the first talk this morning, when you have consumers going to a supermarket, what types of characteristics of the products they buy are important. And that's not the problem I focus on here. It's rather to try to reduce the dimensionality of the large choice set. And in terms of machine learning tools, I must admit there's people in this room that know much more than I do about it. But what we try to do is to apply the method of random projection, which is a tool from machine learning literature, to reduce the dimensionality of the choice set. And this is, as far as we are aware, one of the first uses of random projection in econometric modeling. And Serena Ng, the discussant, has some other work using random projection also. And also it's an example of using machine learning techniques in nonlinear econometric models. Okay, so we're going beyond the linear regression framework. And from the point of view of the econometrics, the model that we want to consider is a semi-parametric model. So it's a model that tries to avoid making very strong parametric assumptions on the random variables in a model. And what we do is we try to use some convex analytic properties of the discrete choice model, which do not depend on particular parametric forms for the random variables, to derive the estimating equations. Okay, so I guess if you remember the first talk this morning, where there was this, the Star Trek cookbook, and then the shoehorn and the duct tape, I feel like you can kind of think these two are sort of the components of this, maybe this kind of new stew that we're trying out, which is random projection mixed with semi-parametric econometric modeling. Okay, so let me just briefly introduce the discrete choice model. So we are, it's a kind of, workhorse model in economics. So we think of consumers, they have to choose one of a number of choices. So their choice set consists of choices indexed 0, 1, 2, 3, so on, up to D. And the problem is that D is, it could be very large. Okay? And so this discrete choice model has a random utility formulation, which is ultimately due back to McFadden. And so the idea is that a consumer making a choice in this environment chooses the product J and the product J yields a utility, which is the sum of two parts. Okay, the first part is this part Uj, which I'm going to call the utility index. Okay, and it depends on product characteristics and prices and so on, which we, the researcher, observe. Okay, so we can call that the kind of deterministic part of utility. And the second part is this epsilon j, which is a utility shock. Okay, and it's a random part of utility. It's different for all the consumers. Okay, and that's why this is called the random utility model. Okay, because even though people face the same utility from buying the product, the choices can be different due to their random part of their utility, the epsilon j. Okay. And so the idea is that facing a choice in this environment, the decision maker is going to choose the utility used, which yields the highest, the option that yields the highest utility. Okay, so it's going to choose the product J such that the utility from product J exceeds the utility from all the other products. Okay, and parameters of interest in this model is this, beta here. Okay, the loadings on the product characteristics. Okay, so I guess going back to the previous talk to Larry's talk, I guess this model, we assume that there is a sort of true model of beta out there, and that the model is a kind of, it's a pretty good description of consumer behavior in this market. Okay, so let me just introduce some notation. So we're going to use epsilon vector to denote the vector of utility shocks across all the choices. U vector to denote the utility indices across all the choices, and then this block X to denote the kind of matrix of product characteristics across all the options. Okay, and then I'm going to introduce this notation of the market share Sj, okay, which is for given utility vector U, it's the probability that product J is chosen among all the products. Okay, so it's a market share or choice probability. Okay. And throughout, we're going to assume that we have access to aggregate data set, which consists of the market shares and the product characteristics, for the different products across a range of markets. Okay. So, are there any questions? I guess I can. Okay, so as far as the assumptions we make, they're pretty standard in this literature. We assume that the utility shocks are independent of regressors, so we don't deal with the endogeneity problem here, which is also an important issue in people estimating these models. One point of departure we make is that we don't want to make a particular assumption for the distribution of this error term epsilon. Okay, so this is a semi-parametric model. So for instance, we don't want to make the assumption that this epsilon is a distributed extreme value, which would lead to the logit discrete choice model. We don't want to make an assumption that this epsilon is Gaussian distributed, which would lead to a probit type of discrete choice model. But we want to leave it unspecified. And this is because from a demand point of view, you don't want to restrict the correlation patterns among the utility shocks for the different goods, because that's going to restrict the type of elasticities that come out of the demand model. Okay. And finally, we have to normalize the utility from one of the choices to 0, and so we normalize the utility from good 0 to 0. Okay. Okay, now first let me just go first and hopefully more quickly into the first component of this model, which is the estimating inequalities. Okay, now since we don't specify a particular distribution for the epsilons, parametric discrete choice models like logit or probit and so on, they aren't appropriate here. Instead, we're going to estimate these the model, the parameter beta, just exploiting some inequalities, which are derived from some what I would call meta properties of this model. So they hold, there are properties of the model which hold regardless of what the distribution of epsilon is. Okay, and there are properties derived from the underlying convexity of the model framework. Okay. Now, the idea is the following, that we introduced this function g of u, which McFadden in the literature calls the social surplus function. It denotes the expected maximal utility that a decision maker makes in this setting. Okay, so if a decision maker chooses good j, he gets utility uj plus epsilon, right? And so the consumer is going to choose the utility, the good that leads to the maximal utility, and so that's the max, right, of uj plus epsilon j. And the expectation of that random variable is going to be what's called the social surplus function. Okay. Now the important thing here is if you view this function as a function of the vector of utilities, this function is convex in U, okay, because of the convexity of the maximum operator. Okay. And it's also another well-known property in this class of discrete choice models that the market shares, corresponding to a given vector of utility indices, is just correspond to the gradient of this social surplus function. Okay, so for those of you who know consumer theory, this is a little bit like Roy's identity, but in a discrete choice model setting. Okay, it's a relationship between the demand functions and the underlying welfare function. Right? And so we're going to derive estimating inequalities from this property of the market shares, that they are the subgradient of the social of a convex function, basically. Okay, and so what are these estimating inequalities? They are derived from a particular monotonicity condition. So I guess the intuition is kind of simple. If you have a single-variate convex function, then the slope is monotonic, right? So if you have a multivariate convex function, which is what the social surplus function is, then there's still a monotonicity relationship of the gradient. But in this case, because it's the gradient is a vector, you can't talk about just monotonicity. There's different ways of talking about monotonicity, and the way that is right is called cyclic monotonicity. Okay, and so let me just define it now, and maybe I'll give you a little more intuition later. Okay, but the idea is the following: that if you consider a cycle of markets, okay, so consider a sequence of markets 1, 2, 3, where the last element of the sequence is the same as the first element. Okay, that's the cycle. Then actually, if you sum the difference in utilities across the cycle times the market share, okay, that if you sum this across the cycle, it has to be less than or equal to 0. Okay, that's what cyclic monotonicity means. Okay, and so we're actually going to use these inequalities as the basis for estimation. Okay, and so you look at, if you plug in the specification for the utility indices, then you see that these inequalities, they're linear in beta, and they don't involve the epsilons at all anymore. Okay, and so they can be used to identify and estimate this beta parameter in a semi-parametric manner, in a manner which does not require assumptions to be made about the distribution of the epsilon. Okay, and the important thing from an applied point of view is that these inequalities are valid even when some of the market shares are equal to 0. Which is, of course, going to be very likely when you have a very large data set with a lot of different options. There's going to be a lot of choice probabilities, which, at least in the data, are equal to a 0. Right? And that's been a problem for applied researchers. But here, it doesn't really matter because that's accounted for in these estimating inequalities. Or that's allowed for in these estimating inequalities. So there's a lot of, this is empirically relevant. And also, recently in economics, there's been a focus on kind of behavioral models of decision making, like rational inattention or consideration sets, which actually will lead decision makers to choose certain options with probability 0. Okay, so they arise both from a theoretical framework, setting as well as an empirical setting. Okay, so now let me talk about the second component of this work, which is the machine learning component. And so the problem here is that the dimensionality of these vectors, the vector of utility indices and the vector of market shares, they're actually very large dimensional. Because remember, the dimensionality of these vectors is the number of products in the market, right? And there's too many products in the market. Like there's too many locations in Manhattan. There's too many restaurants in New York City. Okay, so what we want to do is we want to kind of project this dimension down. And what we're going to do is use this tool called a random projection. Okay, so what we're going to do is what we want to do is project down vectors in d-dimensional space down to k-dimensional space, where k is hopefully much smaller than d, right? And so in particular, how does random projection work? Well, we start with a large dimensional, a d-dimensional vector y, okay? And we introduce a matrix of random variables, which we'll call R. And the dimensionality of this random matrix is k by d. Okay, so the number of rows is much smaller than the number of columns, right? And so the random projection is just given by the pre-multiplication
of this large high-dimensional vector y by this random matrix R. Okay, and so that will, of course, lead to a vector y tilde, which is smaller and much smaller in dimension, right? It's just k by 1. Okay? And the literature has pointed out many possible candidates for this random projection matrix R. What we're going to do is consider what's called sparse random projection, okay, which is a case where the random elements in this matrix R, they can be equal to 0 with some perhaps very high positive probability. Okay, and so so basically you can see what's going on here is that the weight is, so we're going to give a positive weight to some elements, negative weight to some elements, and 0 weight to some elements, right? And depending on the size of this constant psi, the weight that we give to 0 can be calibrated to be larger or smaller. Okay, so psi here measures the sparseness of the random projection. And so just as an example, if we have 5,000 choices and psi is set equal to the square root of d, then we're actually only, in pre-multiplying by r, we're actually only using kind of 2% of the products. We're sampling only 2% of the products. So let me just, before going on, I just want to give some properties of random projection. And again, there's people in this room who know much more than I do, and so I'd like to sort of give that as a caveat. But I guess there's some nice some interesting features of random projection which give you some intuition for why it works. First is that basically random projection preserves length, right? In the sense that if you consider the large element, the length of the high-dimensional vector y, okay, the length of the lower-dimensional vector y tilde is in expectation, now because this is a random vector now, right, conditional on this one, the expected length of the projected vector is basically equal to the length of the original vector. Okay, and the variance of the projected vector is an order 1 over k, where k is the reduced dimension. Okay, so basically what random projection is doing is it's replacing the high dimensional vectors with lower dimensional vectors which stochastically have the same length, okay, in expectation. And the use of random projection then is justified by it's called the Johnson-Lindenstrauss Theorem. Okay, and so I guess as I understand, the Johnson-Lindenstrauss Theorem is something like the Folk Theorem in economics. Okay, it's something that everyone knows, but people define in slightly different ways. Okay, and so just here's one statement of the Johnson-Lindenstrauss Theorem. So let's consider the case where you want to project down a high-dimensional, d-dimensional vector w down to a k-dimensional vector, much lower, w tilde. Okay, and what does this Johnson-Lindenstrauss result says? It says there exists a mapping from Rd to Rk which preserves Euclidean distances among the points. Okay, so let's say we have capital M points, which are the number of markets in our data set that we want to project down. Okay, for every pair of points, so let's consider a pair with index M1 to M2. We have for some constant delta, which is less than a half, and some value of k, which is a function of the number of points you want to project down, and also the delta we want to consider. And then we have the following inequality. And what's the inequality saying? It's saying that the distance between the lower dimensional vectors, which are these two w tildes here, lies within a delta neighborhood of the distance between the high dimensional vectors. Right, so again, the idea of random projection is to preserve length, right? So basically, the distance between the two projected vectors, w tilde m1 and w tilde m2, is bounded, within a delta neighborhood of kind of the true length of the high-dimensional vectors. Okay, and the important thing here is that the proof of this theorem, at least most of the proofs I've seen, they are probabilistic. Okay, and why that's important is that this motivates the use of a random projection in achieving this bound. Okay, there's no, as far as I know, there's no deterministic characterization of what this mapping is, but the proof is probabilistic, which allows us to try to achieve achieve the bound by taking random projections. And so that's exactly what we do. So I want to just define what I'll call just the RP, a random projection estimator. So again, we have the original data set, which is high dimensional. Right? Each of these vectors has dimensionality d, which is very large. And I want to project it down to what I call this data set d tilde, where all the vectors in the original data set have been pre-multiplied by a random projection vector. And so now they are all lower dimensional vectors in RK. Okay? And so what I'm going to do then is I'm going to go back to the inequalities that I use for estimating, and instead of the true values, the high dimensional values for the x's and the s's, I'm going to just plug in the lower dimensional projected versions. Okay, and so this is going to be the projected version of the cyclic monotonicity inequality. And then what I'm going to define as our estimator, the random projection estimator, is that we are going to just minimize a criterion function, which is the sum of the squared violations of these inequalities. Okay, so for each value of, and we sum this across all the possible cycles, right? Since this inequality has to hold across all cycles across markets, we sum across all cycles, and so whenever an inequality is violated, we square that violation, and that enters our criterion function. Okay, and so a convenient thing for optimization is that it turns out this criterion function is convex in beta, which is convenient for optimization. But the thing is, of course, since we are estimating based off of inequalities, we might have multiple optima. So we don't necessarily have point identification. It could be partially identified. Okay. Any questions? Okay, so now let me just go quickly over some properties of this random projection estimator. So the first is sort of why does random projection work for our model? Because it's not clear what the relation between Johnson-Lindenstrauss and random projection is and discrete choice. Okay? And it turns out that random projection, it works for our model because it turns out these inequalities, which form the basis of how we estimate in this model, they can actually be rewritten in terms of the Euclidean distance between vectors. Okay, so basically this inequality here, if you do some simple algebra, you can rearrange it to have the same form as here, and you see that this form of the inequalities is written exactly in terms of squared Euclidean distances between vectors, right? So hence, by the Johnson-Lindenstrauss theorem, since the random projection preserves Euclidean distance, if the elasticities, if the inequalities are satisfied in the original data set D, they should also be approximately satisfied using the projected data d tilde. Okay, and so that's why random projection works here. So I guess the idea here is that random projection might not work for all econometric models because the virtue of random projection is that it preserves Euclidean distances, right? And there's a lot of nonlinear econometric models where a lot more than distances between Euclidean distances matter, right? But of course, for least squares regression, there's no problem because x prime x inverse x prime y is leads to the same value. Basically, it's written. It's just function of Euclidean distances between those vectors, right? So it works so random projected regression works, but not random projected dynamic discrete choice model or something like that. Something very complicated. Okay, now some more properties of the random projection estimator. So you see that from the point of view of the randomness here, this random projection estimator, beta tilde, is random due to two sources. First is just the inherent randomness in the random projection, that this R matrix is a matrix of random variables. And the second thing is that there's also randomness in the data, right? The market shares that we use in estimation are also, you can think of them as random variables. And for the purpose of this talk and the kind of simulations I'm going to show you later, I'm going to ignore the second kind of randomness because I'm going to assume that the data is perfect. And that's actually not far off, given that we consider aggregate data. And in aggregate data, these market shares are typically computed from a large number of consumers. And so the sampling error could be quite small. And so we'll just focus on the randomness due to the projection itself. But for inference, there's a lot of open questions. I think this is in the previous talk I was raised up. So what we're able to do in the paper is show uniform convergence of the kind of criterion function using the projected data to the criterion function using the true data. Okay, now remember the data itself has no noise. as the dimensionality of the projection grows, right? And of course, this uniform convergence in a criterion function is going to be a useful building block for showing nice properties of the estimator, like consistency and so on. But for inference, for further inference, there's actually, we couldn't find much guidance from the machine learning literature. But of course, I know much less. And so if there's anything, I'm happy to hear more about it. So what we do in practice is we try to do what we've seen done in some of the machine learning papers, which is to assess the performance of the random projection estimator by doing the random projection a lot of times and seeing how the estimate for beta changes across these different random projections. Okay, so it's kind of a way of assessing how the stochastic element in a random projection affects the estimates that you get. Okay, so let me just go quickly over this. I have some Monte Carlos and also 2 applications, but obviously I'm not going to get to all those. So let's see how far we get. So as far as the Monte Carlo simulations, what we do is we try a discrete choice setting where the size of the real size of the choice set ranges between 100 and 5,000, and we project it down to these different values, like 10, 100, or 500. Okay? And we consider 30 different markets in our data set. Okay? Now, in each design, like I said before, we're going to fix the data, so we're not going to vary the data across replications, but we're going to across replications, we're going to redraw the random projection matrix. And we're going to report the results across these different draws of the random projection. And as far as the utility specification, we assume there's 2 x's. The x's are Gaussian distributed. And in these class of semi-parametric models, it turns out you have to normalize the norm of the parameter vector beta. And so what we're going to do is is going to estimate everything in terms of polar coordinates. So everything at the beta 1 and beta 2 can be written in terms of this one parameter theta, which is arbitrarily set equal to this value here. So that's a true value. Now, as far as the random error structure, epsilon. Remember, we are using a semi-parametric approach, so we can be, quite flexible with what we do for the epsilon. So we do something maybe a little bit, too flamboyant. I don't know. But what we do is we assume that there's a kind of MA2 serial correlation and errors across products. Okay, so obviously that doesn't correspond to the multinomial logit model. It's not an exchangeable distribution. It's something it has not really any meaning either. But it's just to kind of highlight the what our model can handle, I guess. And in terms of the cyclic monotonicity, we only consider cycles of length 2 and 3. So you don't go up to cycles of length 15, 16, 17, so on, even though we could, just for computational issues. And as far as the results, they're in the table here, but let me just summarize them due to time. So first of all, the results are robust to different ways of specifying the random projection matrix. So we tried basically different values of this psi tuning parameter, including psi equals 1, which is the dense case, where you sample all the options with positive probability, to square root of d, where you sample only around 5%, 2% of them. And in most cases, when we optimize the criterion function, it yields a unique minimum. So we don't seem to get, at least in this study, any type of partial identification. And so you see that here. So in these designs, we always, across all 100 random projections, we always get a unique minimum for the criterion function. Except, of course, there's some variance across the 100 different random projections. But in these 3 designs here, there's some partial identification, that there's a range of values of beta which set the criterion function to a 0, basically. Okay, and so on average, the estimates, if you just compare the true value, is 2.3562. Overall, I would say we're pretty close, but it's kind of hard to judge because it's not clear how to interpret this kind of standard deviation across random projections. So I think there's, I think one thing here is that, this is still very much, I think, a little bit work in progress or proof of concept because the inference is not quite nailed down yet. Okay. Now, as far as the applications, let me just, I've, I guess, 7 minutes. Let me just go quickly over this. So we used the, in honor of this being in Chicago, I guess, we used this venerable Dominic's supermarkets data set. I guess it's so venerable that Dominic's went out of business 10 years ago and people still use this data set. Rest in peace, Dominic's. And okay, and so consumers choose both the So what we do is we estimate a model where consumers jointly choose the store they want to purchase at, as well as the soft drink to buy. And this kind of leverages the approach, again, of our semi-parametric framework, because typically if you want to estimate a model of joint store brand choice, you would model it as a kind of tiered discrete choice model, like a nested logic model. But in our approach, there's no need to specify the tiering structure, okay? Because the problem in estimating nested logic model is typically you have to decide, oh, do consumers choose first the store and then the soft drink? Or do I choose first the soft drink or the kind of soft drink I want to buy and then decide the kind of store I want to go to? Here, there's no need to specify that because we have the semi-parametric approach, which allows both, which allows for either. We can be agnostic about that. Okay, and as far as the so our markets, our markets are actually going to be time periods. Okay, so the data sample is from October 96 to April 97. So we split those into 2-week periods, and each of those as distinct markets. Okay, that's how we do it. And so in this store brand model, the consumers can choose among 11 Dominick supermarkets, which have different. Some are premium tier, some are medium tier. And so a choice is a combination of the store that the consumer goes to, as well as a particular UPC, a product code that they buy. And so using the data set on soft drinks, it turns out there's the choice set has dimensionality 3060. Okay, so again, that's not super large, but I would say for a lot of I/O or marketing applications, that would be pretty large. Okay? And we reduce this down to 1/10 using random projection. And again, we report the results from 100 independent random projections. So let me just, so the variables we use, there's the market share, and then the control variables, we have the price. We have, whether the product was put on promotion. We have, we have dummies for holiday periods, Christmas and Thanksgiving, and then also some store characteristics. Okay, so let me just summarize the results. First, we find that when we minimize this criterion function, it's always uniquely minimized. So there doesn't seem to be, at least in the data, a partial identification issue. But the estimate that we get does vary across the different random projections. So let me just show you the flip back and forth. So in the brackets, I give you the 25th to 75th percentile of the estimates across the 100 random projections. So you see for some parameters, like the price parameter, the interquartile range is tighter than for other parameters, like the store characteristic parameter. Okay. Now, as far as the substantive results, we find that purchase incidence is decreasing in price, which makes sense, I guess. Demand curve is downward sloping, and it's higher, if the product is on promotion, which again kind of makes sense, and it's also higher during holiday seasons. I guess people buy Coke during Christmas, and we also find that we also allow for some interactions of price and these different variables. When we find that the price coefficient is negative and also lower on discounted items. So it seems to indicate that kind of consumers are more price sensitive when items are on discount. Okay, and then also the price sensitivity is also the price sensitivity also increases during the holiday season. So people somehow, when they're buying soft drinks for the holidays, they're more sensitive to price than otherwise. And I guess my interpretation of this is that during holidays, I'm buying Coke for, my wife's friends who visit, and I don't really care. I want to buy the cheapest thing for them. And, but during other seasons when I'm the one drinking the stuff, I'll buy the good stuff for myself. So maybe that's the reason. And then, there's no effect of the store variables. But again, you see that, it took us a while to get these results, and there's still a lot of, kind of some questions. It's obviously not, there's still a lot of work to be done as far as, and especially in this matter of inference. We're not really sure how to consider whether the results are, are tight or not. Okay, so let me, I think that's it. I have another application to mobile advertising, but I think you can always ask me about that later. Let me just conclude with some remarks. First is that the one thing we like about random projection estimation is that actually, in principle, all that we need is the projected data set d tilde. We never need the original data set, right? Unless we are doing this kind of this thing of doing repeated random projections and so on. So in principle, if privacy is a concern, then the people who have the data, they could just give us this d tilde, and we could already, we could already estimate the model. And so that's a nice aspect of random projection. And there's also different approaches. There's also an existing literature in econometrics on semi-parametric discrete choice models, but let me not go too much into that. Okay, let me just conclude then. So what we try to do here is consider a problem which is, I think, becoming more prominent in applications of discrete choice models, which is the choice set is very large. And what we do here is we try to use this tool from machine learning, a random projection, for dimension reduction of these models. And we consider a semi-parametric estimator, which does not rely on specifying a particular functional form for the distribution of the utility shocks. And the procedure shows promise, I think, in the simulations and in the real data applications, but obviously there's still much more work to be done, especially on the kind of thinking more on inference and so on. And we think actually random projection may also be fruitfully applied in other econometric settings. I'm happy to hear any suggestions anyone might have. Thank you.